Good morning. Myself, Professor Sangeeta Gupta from CBIT Hyderabad. Today, we are going to discuss about the different instruction code formats associated with the computer. So, the basic computer has three different instruction code formats. They are memory reference instructions, register reference instructions, and input-output instructions. For each and every instruction format, the size of the instruction is taken as 16 bits from 0 to 15. Out of the 16 bits, a memory reference instruction is identified by 0 to 11 bit. That is, total 12 bits are used to represent the address. And the opcode bit from 12 to 14 takes the values from 3 binary bit zeros to 3 binary bit 110, that is a representation for 6. Hence, the opcode bit can vary from 000, 001, 010, 011, 100, 101, and 110 with respect to different memory-based operations. The last bit is the mode bit, which represents whether there is a direct address or indirect address. So about the direct and indirect addresses, I have discussed in my video on addressing modes. Then the other categories of instructions are register reference instruction and input-output instruction. In register reference and IO instructions, the bits 0 to 11, that is a total 12 bits, are used to represent either the register operations or input-output operations because we don't have a need to fetch the data from memory. Hence, instead of representing the address, we are representing the direct operations which are related to either register or input-output. Then coming to the bits 12 to 14, which represents the opcode, here the opcode bit for both of the instructions is represented by 111, which is a binary equivalent for the decimal 7. We are differentiating the register operations and input-output operations based on the 15th bit, where if the 15th bit is 0, then the instruction is identified to be a register reference 1. If the 15th bit is 1, then the instruction is identified as an input-output 1. These three are the basic instructions associated with any computer instruction. So, to brief out, in memory reference instructions, we have 12 bits to represent address, 3 bits to represent opcode, which takes the values from decimal 0 to 6, and the last bit is the mode bit, which represents either direct or indirect address. Then the register reference instructions do not have an address field. In fact, the bits 0 to 11 are used to represent the type of register operation, and the opcode is identified by using 3 ones, which is the decimal 7, and the 15th bit is 0. Input-output operation is identified as 0 to 11 used for representing IO operation but not any address. 12 to 14 opcode bits are 1, which is the binary equivalent for decimal 7, and the 15th bit is 1. Now, to understand these instructions in detail, we have different register reference instructions such as setting sequence counter to 0, which is also known as clearing the sequence counter. Clearing the accumulator is also a category of register reference instructions. Then clearing the E, which is an extended accumulator or a 1-bit flip-flop, is also a register reference instruction. Apart from these clear instructions, the three instructions are taken as clear instructions. We also have the complement operations, complementing the contents of accumulator, and complementing the E flip-flop are taken as complement instructions. In addition to these, we also have the shifting operations, that is circular left shift and circular right shift. In circular right shift, we are shifting right by one position the contents of accumulator, and the bit in the 15th position of accumulator is obtained from E flip-flop. This E flip-flop in turn obtains its value from the 0th bit of accumulator. Hence, in a circular fashion, without leading to any loss of bits, we are trying to shift the bits by one position to the right side. Similarly, in the circular left operation, we are shifting left the contents of accumulator by one bit position. Hence, the bit in the 0th position of accumulator is obtained from E flip-flop. The 15th bit of accumulator is in turn moved to E flip-flop. Hence, here also, without leading to any loss of information, the bits are circulated by one position to the left side. Next operation is incrementing the contents of accumulator, which is represented using AC plus 1. The next four instructions are based on skipping instructions. So the first two instructions are where we are trying to skip the accumulator by if the 15th bit, that is the sign bit, is 0. So if the sign bit is 0, then we are skipping the current instruction and going ahead with the next instruction, represented as if AC of 15 is 0, then PC points to PC plus 1. It is to note that PC already contains the address of next instruction. So by using this skip instruction, we are not fetching the address pointed to by PC, but in fact, we are further incrementing PC to 1. Similarly, skip if negative is represented by the sign bit 1 in the 15th bit position of accumulator. And then if the contents of accumulator are 0, in that scenario also, we have an instruction that is SZA, which is skip if accumulator is 0. And similarly, if E flag contains 0, then also we can use the instruction SZE, which indicates skip if E is 0. After execution of all the register reference instructions, we can halt the computer by setting 0 to S, which is a start and stop flip-flop. So these are all the register reference instructions. Now, moving on with the memory reference instructions, we have 7 categories of memory reference instructions. The first operation is an AND operation. AND operation is performed in between the contents of accumulator and the memory word present at an address located by address register. However, it is to note that the contents in memory has to be fetched into some temporary data register, and then we can perform AND operation with the contents of accumulator and push the result back into accumulator. Similarly, to perform add operation, we are adding the word present at a memory location with the contents of accumulator, and the result is once again fetched back into accumulator. There is a load instruction where we are loading the contents into accumulator from a memory word specified at a particular address. During add operation, wherever there is a carry, the output carry bit is moved into E flip-flop. And during load operation, we are trying to load the contents, fetching it from memory and loading it into accumulator. The next instruction is store accumulator, where we are trying to load the contents of accumulator into memory word specified by a particular address at AR. The next three instructions are used to alter the sequential flow of execution, that is branch unconditionally, branch and save return address, increment and skip if 0. So in branch unconditionally, without occurrence of any condition, we are trying to branch to the location. Okay, so in branch unconditionally, without the occurrence of any condition, we are updating the address AR with the address present in PC. The other instruction branch and save return address is used to indicate where program may have various functions or subroutines, and the transfer of control from main program to the subroutine and again returning back to the program where it has left is represented efficiently with the help of branch and save return address. Here we are updating the PC with memory word present at a particular address, and then the address register contents are incremented by 1 and then fetched to PC. So these variations are used to indicate that we are transferring the control to a subroutine execution, and then we are returning back to the place where we have left after execution of the subroutine. The last instruction of memory reference is ISZ, increment and skip if 0. So here, if the contents of memory word is resulting in 0 after incrementation, then we are skipping the current instruction and proceeding with the next instruction. So there is a possibility of the memory content being 0 only if we are working with signed integers or negative numbers. The last category of instructions is input-output instructions. So these input-output instructions are related to performing operations on the input and output registers. So it is necessary to note that the size of input and output registers is 8-bit. Hence, the accumulator, which is of 16 bits, does not use all the 16 bits to deal with the input and output contents. Hence, the lower order 0 to 7 bits, which represents total 8 bits, are used to operate with input and output registers. When working with the input and output registers, we are also trying to set the values of flags, that is input flag and output flag. So these instructions initiate with clearing the sequence counter to 0, and then whenever we are performing input operation, the contents of input register are moved into the lower order 8 bits of accumulator. At the same time, the input flag is set with 0. When performing the output operation, the contents of accumulator are flashed into the output register and output flag is set to 0. Whenever we wanted to perform a skip operation on these input and output contents, then to perform skip on input flag, the content of FGI, that is input flag, is checked. If the content is equal to 1, then we are skipping the current instruction and proceeding with the execution of next instruction. Similarly, by looking at the content of the output flag, if the output flag is 0, then we are skipping the current instruction and executing the next instruction. There are other two instructions associated with interrupt. So interrupt is basically a hardware implementation of branch and save return address. There are two important instructions associated with an interrupt, that is interrupt enable on and interrupt enable off. So interrupt enable on is basically performed whenever the content of IEN, which is an interrupt enable flag, is set to 1. Interrupt enable off is performed whenever the content of IEN is reset to 0. To brief out, in this video, we have seen about the different memory reference instructions, register reference instructions, and input-output instructions. Thank you for watching. Please like, share, and subscribe my video.